Let us continue our lectures on optimization for data science. In this lecture, we will look at multivariate optimization, nonlinear optimization. However, in the previous lectures, we saw the unconstrained version of this problem. In this lecture, we will look at problems of this type where we have what are called equality constraints. I will explain what that is presently. And I am going to explain this using a very simple example. But before we dive into this example, let us set some context and then ask the question as to why we should be interested in this in a course on data science. The reason why we are interested in constraints in optimization is, as I mentioned before, we look at optimization from a data science viewpoint because we are trying to minimize error in many cases when we try to solve data science problems. And when we minimize error, we said we could use some kind of gradient based algorithm, what we called as the learning algorithm, to solve the problem. In some cases, while we are trying to optimize or minimize our error or the objective function, we might know some information about the problem that we want to incorporate in the solution. So, if for example, you are trying to uncover relationships between several variables and you do not know how many relationships are there, but you know for sure that certain relationships exist and you know what those relationships are, then when you try to solve the data science problem, you would try to constrain your problem to be such that the known relationships are satisfied. So, that could pose an optimization problem where you have constraints, in particular equality constraints. And there are several other cases where you might have to look at the constrained version of the problem while one solves data science problems. So, it is important to understand how these problems are solved. Once we look at equality constraint problems, we will look at inequality constraints, which is even more relevant. For example, the algorithms for inequality with inequality constraints are very useful in a data science algorithm that is called support vector machines and so on. So, we are going to look at both equality and inequality constraints. Now, let us look at this problem right here. So, we are interested in minimizing the function here, which is 2x1 squared plus 4x2 squared, and like we discussed before, this is an objective function in two variables x1 and x2. So, a real visualization of this would be in 3 dimensions, where the objective function value is plotted in the z direction. However, we know that we can work with contour plots, and if you look at this picture here, you see these contour plots. These are plots where each of these contour is a constant objective function contour, and again you would see that these are ellipses, because if you look at constant contour plots, then you have 2x1 squared plus 4x2 squared equal to k. This you will see is an ellipse, that is what is plotted here. Now, if you look at the optimum value for this function, just by inspection, you can see that the optimum value is 0, because these are functions where I have terms which are squares of the decision variables. So, there are 2 terms here, 2x1 squared plus 4x2 squared, and the lowest value that each one of these could take has to be 0, and that basically means the unconstrained minimum is at x1 equal to 0, x2 equal to 0. The objective value at that point is also 0. So, which is what is shown here in this point right here. So, if I had no constraints, I would say the optimum value is 0 and it is at 0 0, the star point here. Now, let us see what happens if I introduce a constraint. In this case, I am going to introduce a very simple linear constraint. So, let us assume that we have a constraint of this form, which is 3x1 plus 2x2 equals 12. Now, what this basically means is the following: you are looking for a solution to x1 and x2 which also satisfies this constraint. Okay, that is what it means. So, though I know the very best value for this function is 0 from a minimization viewpoint, I cannot use that value because the 0 0 point might not satisfy this equation. So, you will notice that if I put x1 equals 0, x2 equals 0, it does not satisfy this equation. So, the unconstrained solution is not the same as the constrained solution. Now, let us see how we solve this problem. To understand this, we first start by representing this constraint in this two dimensional space. So, since this is a linear constraint, you will see that it is a line which is here, which is what is given by this constraint. Now, since we said that whatever solution I get, it should satisfy this constraint, would translate to saying I can only pick solutions from this line, because only points on this line will satisfy this constraint. Now, you notice that you could pick many points on this line. So, for example, you could pick this point, and the objective function value at that point would be corresponding to a contour which intersects this point. So, if you pick a point here, then you would have a corresponding objective function value. Now, you could pick a point here, then you would see that you would have another objective function value which would be corresponding to the constant function contour that intersects the line at that point. So, you notice that as you pick different points on this line, the objective function takes different values, and what we are interested in is the following: of all the points on this line, I want to pick that one point where the objective function value is the minimum. To understand this, let us pick 2 points and see what happens. So, if I pick a point here, and let us say I pick a point here and ask the question which one of these points is better from a minimization of the original function viewpoint. The way to think about this is the following. So, when I pick a point here, I know that the objective function value would be based on the contour which intersects at that point. And if you compare these 2 points, you will see that this point is worse off than this point from a minimization viewpoint. This is because if you look at these contours, these are contours of increasing objective function values, and the contour that intersects this point is within the contour that intersects the line at this point. So, basically what that means is, because this is the direction of increasing objective function value, the contour intersecting this point is inside the contour intersecting at this point. So, that basically means this function takes a lower value at this point on the line. So, as you go along the line, you see that the value keeps changing, and my job is to find that particular point where the objective function value is the minimum. So, this is a basic idea of constrained optimization solution that we are looking for. The key point to notice here is that the unconstrained minimum is not the same as the constrained minimum. If it turns out that the unconstrained minimum itself is on the constraint line, then both would be the same, but in this case we clearly see that the unconstrained minimum is different from the constrained minimum. So, when I have just only one constraint, how do I solve this problem? I will first give you the result and then explain the result again by going back to the previous slide and then showing you another viewpoint and then how that leads to this solution. So, if you typically take a multivariate function f of x, in the unconstrained version let us assume that x is x1, x2 and xn. We know that the optimum solution is grad f equals 0, which basically means that dou f dou x1 dou f dou x2 all the way up to dou f dou xn equals 0. So, this when I expand this further, I will get equations dou f dou x1 equals 0, dou f dou x2 equals 0, dou f dou xn equals 0 and so on. Now, notice that if there are n variables, there will be n equations of this form. So, I have n equations in n variables, I can solve for it and find a solution, and once I find a solution to find out whether it is a maximum or minimum or a saddle point, I calculate the second derivative and then construct the Hessian matrix, and then depending on whether the Hessian matrix is positive definite, positive negative definite or semi definite and so on, we can make judgments about whether the point is a minimum point, maximum point and so on. Now, let us see what happens if I am trying to solve a problem where I have minimized f of x, which is x1, x2 all the way up to xn, but like I said before, let us assume that I also introduce one constraint, and I am going to introduce let us say a constraint which is of the form h of x1, x2 all the way up to xn equal to 0. So, this is an equality constraint. So, we can always write a constraint in this form, even if you have some number on the right hand side, you can always move it to the left hand side and write this constraint as something equals 0. So, basically my job is to find the minimum point for f subject to this constraint. I will just give you the result and then we will see how we get this result. So, when I want to solve for this problem, the result is in this case grad f equal to 0 itself gave us the result. In this case it will turn out that the result is the following. So, we can write the negative of grad as to be equal to some lambda gradient of h. Okay. So, you can write this as negative or drop the negative, and the sign of the value lambda will take care of that, but I am writing in this particular form. So, just to expand this basically says okay, I have something like this, I have dou minus dou f dou x1 all the way up to dou f dou xn equals lambda dou h dou x1 all the way up to dou h dou xn. So, if you expand this further, I am going to get n equations. In this case I got these equations to be 0. In this case I am going to get equations of the form minus dou f dou x1 equals lambda dou h dou x1 will be one equation. The second equation will be minus dou x2 equals lambda dou h dou x2 and so on. The last equation will be minus dou f dou xn equals lambda dou h dou xn. So, now notice much like before I have n equations, the difference being in the unconstrained case I had zeros on the right hand side, in the constrained case I have these terms on the right hand side. Nonetheless, these equations are in now n plus 1 variables, okay, because I have my x1, x2 all the way up to xn, and I have also introduced a new variable lambda right here. So, my equations are in n plus 1 variables. I have only n equations at this point, but notice that I have one more equation that I need to use, and that equation is the following. If I find some solution x1 to xn which satisfies all of these equations, then that also has to satisfy the constraint, right. So, here we are only talking about the gradient form of the various functions, but the equation which represents the constraints also needs to be satisfied by any solution that we get for the constraint optimization problem. So, with this n equations I will also get another equation which is that h of x1 x2 xn has to be equal to 0. Now, you notice that in this case with one linear constraint I have n plus 1 equations in n plus 1 variables. So, I can solve this. So, to reiterate, the difference between the constraint and the unconstrained case was, in the unconstrained case we had n equations in n variables. In the constraint case with just one constraint we have n plus 1 equations in n plus 1 variables. Now, you might ask what happens if there is more than one constraint, if there are let us say two constraints. So, we will see what happens if there are two constraints. So, in this case we are going to minimize f of x, and now let us say we have two constraints, we are going to say h1 x equal to 0, h2 x equal to 0. In this case what is going to happen is the following. The solution to the constraint optimization problem is going to be minus grad f equals lambda 1 grad of h1 plus lambda 2 grad of h2. So, if you look at this and the one constraint case, you will see the similarities. In the one constraint case we introduce one extra parameter, in the two constraints case we introduce two extra parameters. In the one constraint case we simply said grad f minus grad f equal lambda grad h. In this case this lambda grad h becomes a sum of lambda grad h1, lambda 1 grad h1 plus lambda 2 grad h2 and so on. Now, if there are three equality constraints then you would have three terms here, and if there are L equality constraints you will have something like this here, where this is a sum of L terms. Okay. So, that part is clear. The other part that we need to worry about is if I have enough equations to solve for all the variables. When I have two constraints, that basically means I have introduced two new variables, lambda 1 and lambda 2. However, this equation irrespective of the number of equality constraints you have will always be n equations, right, because grad f would be dou f dou x1, dou f dou x2, dou f dou xn. So, these are all n by 1 vectors. So, this will just give me n equations. Nonetheless, if I had two equality constraints, I need to find the two extra equations which are directly given by the constraint. So, since the optimum point has to satisfy both the constraints, I get one extra equation h1 x equals 0 and the other extra equation h2 x equals 0. So, if I have two equality constraints in n variables, I will have n plus 2 variables and n plus 2 equations, and we will always find this to be true, because if I had three constraints, equality constraints, I will have n plus 3 variables which would be x1 to xn, lambda 1, lambda 2, lambda 3, and this gradient equation will always give me n equations, and the 3 extra constraint would have given me the 3 extra equations. So, I will have n plus 3 equations, n plus 3 variables, which can be directly generalized to this form where I have L equality constraints. So, let us see in the single constraint case how we get an expression like this. That would be easy to see in the single constraint case. This expression where we have the sum of these terms is slightly more complicated to understand. I am not going to do that. I am going to give you an intuitive feel for why this is true in the single equation case, and once you understand that with a little bit more effort, you should be able to think about why it should be true for more equality constraints and so on. So, we go back to the previous slide, and when I was discussing this slide and explaining how equality constraints affect the optimum solution. I said there are many points on this line which could all be feasible solutions. Feasible solutions meaning those are all solutions which can satisfy this equation. Nonetheless, there are some points out of those, or one point which would give me the lowest objective function value. So, when we looked at candidate solutions for this optimization problem, we were looking at the points on this line that we are interested in, because that is a constraint. Now, let us take a slightly different viewpoint and then look at the same problem from an objective function viewpoint. Now, from an objective function viewpoint, if you did not constrain me at all and you said you could do anything you want, then I would pick this point as a solution. Now, when you look at this point and then say, well, this is the best point I have, let me find out whether it satisfies my constraint, and then you substitute this point into this and then you figure out it does not satisfy the constraint. So, you say, look, I have to do something because I am forced to satisfy the constraint. So, you will say, okay, let me lose a little bit in terms of an objective function perspective and then see whether I can meet the constraint. So, when we say I want to lose a little bit, basically you know, as we mentioned before, these are contours where the objective function value increases, and those are actually not good from a minimization viewpoint. So, while I am here, since the constraint is not satisfied, I am willing to lose a little to see whether I can satisfy the constraint, and maybe I go to a point here, okay, and then this is this constant objective function contour point. So, if I am willing to give up something, that basically means I am going and sitting on different points on these contours, and as I am pushed away and away from this minimum point, I am losing more and more in terms of the objective function value, that is, I am increasing the objective function value. Now, logically, if you keep extending this argument, you will see that, let us say this is the first point, I moved here, which is basically worse than this, because you see this is a contour which is going to be outside of this contour, but I moved here, I made my objective function worse, but I still am not satisfying the constraint. So, I give some more, I come to this point and I see a contour, and this point is worse than this because this contour is outside this contour. And if I extend this argument, let us say I keep making things worse, and the only reason I am making these worse is because I am forced to satisfy this equality constraint. So, I come up to, let us say, here, and this is still a contour which is much worse than my original solution, but it is still not enough for me to satisfy my constraint. So, if you keep repeating this process, you are going to find a contour here where I touch this line for the first time, right. So, when I touch this line for the first time is the point at which, for the first time, when I give up my objective function value, I am also able to satisfy the constraint. Now, once I find a contour like that which touches this line, then there is no incentive for me to go further beyond, because going further beyond would mean I would be making my objective function worser. So, when I just touch that line, that is the best compromise, because that is where I become feasible for the first time, and going any further would only make my objective function worse. So, geometrically what this would mean is I keep making my objective function worse till a contour just touches this line. So, at that point this line will become a tangent to that contour, and remember what that contour is. That contour is f of x equal to k for some k. So, we have to choose a k in such a way that this contour, when I have the constraint becomes a tangent to this contour at the optimum point. This geometric fact, when you represent it as equations, you would get the form that I showed, which is minus grad of f is lambda times grad of h. So, this is for the one constraint case. Now, when you have many equality constraints, while it is not as easy to see that as it is in the single equality constraint case, the statement that minus grad f, let us say if I have 2 is lambda 1 grad h 1 plus lambda 2 grad h 2. This statement basically says that this gradient, negative of the gradient, has to be written as a linear combination of grad of h 1 and grad of h 2, and that has a geometric interpretation. So, that is the reason why we get these conditions for optimization with equality constraints. The key point that I want you to remember is that as you have more and more equality constraints, you will have to introduce more and more parameters, lambda 1, lambda 2 and so on. However, there will always be enough equations and variables. So, let us look at a numerical example to bring all the ideas together. We are going to use the same example that we had looked at in the previous slides. So, we are trying to minimize 2x1 squared plus 4x2 squared as the objective function subject to this constraint. So, we wrote the following equations for the optimum point. For identifying the optimum point, we said minus grad of f has to be lambda grad of h, and then we have h of x equal to 0. So, this is what we wrote. Let us do the computation so that we understand this. So, to calculate grad of f, which is basically dou f dou x1 dou f dou x2. So, if you look at this objective function, dou f dou x1 will be simply 4x1 and dou f dou x2 will be 8x2. So, we have grad of f. So, negative grad of f would be negative. Let us look at grad of h. So, h is this equation. So, if I do dou h dou x1 dou h dou x2. So, this is going to be equal to dou h dou x1 will be simply 3 and dou h dou x2 will be simply 2. So, we have this. So, now let us see what this equation becomes. So, this equation you would see is, if you put this in a bracket, and you will see this easily. So, you have the first equation is minus dou f dou x1 equal to lambda dou h dou x1, and we have minus 4x1 equal to 3 times lambda. Similarly, the second equation would turn out to be minus 8x2 is equal to 2 times lambda, and this equation is basically the same equation as the constraint equation that we have here. And as we mentioned before, without the constraint, that would have been 2 variables, and you would have got 2 equations which would have been grad f equal to 0, but with an equality constraint we have added a new parameter lambda. So, we need 3 equations in x1, x2 and lambda. We do have these 3 equations here, and when you solve these 3 equations, you will get this solution, and this is your optimum solution in the constraint case, which is different from the optimum solution in the unconstrained case, which would have been 0 0. So, in other words, we have given up on the value of the objective function. However, this is a point which would satisfy this equation of the line. So, that is how we deal with equality constraints in optimization problems, and I already described how these are useful or why we should study them in the first place from a data science perspective. With this, I will conclude this lecture, and in the next lecture we will look at how we handle inequality constraints, and I will also explain why we are interested in understanding how optimization problems are solved with inequality constraints from a data science perspective. Thank you, and I look forward to seeing you again in the next lecture.